So welcome to this tutorial about electron configuration for ions and something known as excited states. So this video is assuming that you've actually listened to electron configuration and you sort of have a grasp of what it is and understand the fundamentals. Now, when you're determining the electron configuration for ions, you have to be particularly careful that you actually know what the ion is and what charge it has. Because remember, if you take, say, fluorine, and in nature, fluorine, it's very rare to find fluorine in its pure state like that, because we know that fluorine is so electronegative that it will actually grab an electron from the external environment immediately to become stable like neon. Okay, so we know fluorine exists as a negative ion. Okay, so that negative there means that in terms of the electron configuration, fluorine will actually have a different electron configuration in its ionic state rather than this when it's just in its neutral state. Okay, so these are not going to have the same electron configuration, but they will still have 9 protons because proton number doesn't change, but this fluorine here, which is neutral, has 9 electrons. Okay, whereas this fluorine here, which is it's an anion, it's negatively charged, actually has 1 extra electron, which is grabbed from the external environment to become more like neon. So it actually has 10 electrons. And so that's going to mean that these two different versions of fluorine will have a different electron configuration. Okay, so if we look at fluorine's right here. If we just write the electron configuration for fluorine itself, remembering that first we have to fill in the 1s with 2 electrons. So that's the first shell, filling up the spherical, the spherical shape. Maximum of 2 electrons are allowed. Then the second period, so we've got 2s2, again 2 electrons, 1, 2, and then to get up to fluorine we have 1, 2, 3, 4, 5. So the second shell, the p subshell, has 5 electrons. Okay, so this is just for neutral fluorine. Now if we wanted to write it for the ion F minus, it's actually this part is the same, so it's still 1s2, 2s2, and then 2p. Now because I showed you up here that fluorine in its ionic form has 10 electrons, so that means it's grabbed 1 electron from the external environment, so it's actually p6. Okay, so you can see that the two have different electron configurations, however both of them still have 9 protons. Okay, the proton number does not change for the element. Alright, so and I mean the same goes for if you wanted to look at something like maybe magnesium or calcium. We might have a brief look at calcium, just do an example. So we'll have a look at a few more examples in a moment, but calcium can exist in its neutral state as Ca, and it's in its ionic state. If you look at where calcium is, it's right here. Calcium, to become stable, okay, it's a metal, so it wants to lose 2 electrons so it can behave more like argon. Okay, it can have an electron configuration, more of that. It can have a shell, an outer shell that's full, rather than having just 2 electrons sitting there. So actually the ionic form, because you lose 2 electrons, the overall calcium becomes 2+. Okay, again, still calcium in both configurations, in both ionic and elemental state, it has or neutral state, it has 20 protons, but the electron configuration will change. Okay, now if we look at just normal calcium, again, we're going to fill in the first shell, then the second, so 2s2, then the third one, oh sorry, the second shell, but the p, so 2p6. Then we fill in the 3s2, then 3p6. I'm just trying to fit it in here, sorry. And then finally the 4s2. Barely made it. Okay, so that is the electron configuration for calcium. So this is the fourth shell, and you can see, as we mentioned, this group here is the S subshell. Okay, so calcium in its neutral state has 2 electrons being filled into the 4s shell. Now the only difference between this version of calcium and calcium in its ionic form is that it no longer has those 2 electrons at the end here. So it's just 1s2, 2s2, 2p6, 3s2, and 3p6. So that's how you would write out calcium in its ionic state. Okay, so let's then move on to, I had some examples here. We've done a few of them. So I think we've done, have we done sodium? Okay, writing out the electron configuration for the following ions. So sodium, we first need to know what sodium is, so it's Na+. Sulfur is S2-, aluminium is Al3+, and chlorine is Cl-. So if we go back to our periodic table, we know that sodium's right here. Okay, so it has 11 protons. So you can either use the periodic table, or you can just use this filling order that we saw. We don't have to write that 2 up there. So 2s, 2p, 3s, 3p, 3d. I don't think we'll go any further than that, maybe up to 4s. Okay, so we know that sodium is in has 11 protons, but when it's sodium plus, the amount of electrons is 10 electrons. Okay, because overall there are more positive charges than there are negative charges. So if we just fill in this filling order, and use that as the basis, we've got 1s2, so that's 2 electrons there. 4 electrons now, 2 plus 2, and then we have 10 electrons, so the 6. Okay, so this is the electron configuration for sodium ion. Now that will be exactly the same if you were to write out the electron configuration for neon, and it was also the same for when we wrote out the electron configuration for fluorine ion. Okay, so, or fluoride. So just bear that in mind, that with ions, because everything wants to kind of become, in terms of its electron configuration, more like the noble gas, because that's the most stable configuration, then fluorine will move up, gaining an electron to become more like neon, whereas sodium will lose its electron to become more like neon. So you sometimes have the same electron configuration for 3 elements, if not more, because oxygen becomes O2 minus, meaning that it gains 2 electrons to become more like neon. So really a lot of overlap in electron configuration is possible. Okay, so you can have multiple electron configurations for the same electron configuration for multiple ions. Okay, so going to sulfide here, if I just look at the periodic table again, sulfur is number 16, so it has 16 protons, but remember sulfur is a nonmetal and it will try to gain 2 electrons to become more like argon in terms of its electron configuration, so it will gain 2 electrons in addition. Okay, so in a neutral state, sulfur will have 16 protons and it will have 16 electrons, but because the overall charge is negative, it means that there's actually 18 electrons. Okay, so let's draw this out again. So 1s2, so that's 2 electrons. Just following this, that's 4 electrons. That is 10 electrons. We have to keep going until we get up to 18 electrons. So 3s2, that's now 12 electrons. So we have to fill in 3p, 3p6. So 6, we have 12 electrons plus 6, so we have 18 electrons now. And that's the electron configuration for sulfide. Okay, let's have a look at aluminium. So aluminium, where is that? Okay, it's here, number 13. Aluminium is 3 plus. Okay, and that's because it loses 1, 2, 3 electrons to become more like, again, neon. Okay, so what you'll find is that aluminium has 13 protons. The aluminium ion, though, has only 10 electrons because its net charge is 3 plus. So again, we have to get to 10 electrons. So 1s2, that's 2 electrons. 2s2, it's 4. 2p6, that's 10 electrons. So notice how both sodium and aluminium have exactly the same electron configuration. So you really can't tell just by looking at the electron configuration at times what ion you're dealing with. You have to be told a little bit more information. Okay, finally, should be getting this hopefully starting to make sense for you. But chlorine, again, chlorine's number 17, protons. It needs to gain 1 more electron to become like argon. So 17 protons, and it needs 18 electrons. And I think we already had a look at one with 18 electrons. So guess what? Chlorine will have exactly the same electron configuration as sulfide. So 1s2, 2s2, 2p6, 3s2, and 3p6. Okay, so that's just some practice for you there on how to write out these electron configurations for ions. Now, and this is where it gets a little bit tricky. We move on to this concept of excited states and their electron configuration. Now, a lot of neutral atoms can have things, can be in the state called the excited state. Now, there are 2 different types of states. Okay, there's the ground state. and then this excited state. So the ground state is when electrons are filling in the subshells as per lowest energy to higher and so forth. So ground state is the usual, I guess I could write, follows the electron filling order. So it's just the normal behavior of the way in which electrons should fill in the shells. Now the excited state occurs when there's external energy. Okay, so there might be heat present. So you might be taking a sample of atoms and heating them up with a Bunsen burner. Now what that does is it provides external energy. So external energy is provided, I'll write it like that, which means actually that electrons are able to jump to higher energy shells. Okay, so excited states is when electrons jump to higher energy shells due to external energy. So there's external energy, maybe there's light or there's some kind of thermal energy, etc. And so I'm just making up an example. So maybe you have this kind of filling order. And there's an electron filling that one, but then it jumps, another electron jumps to here. And now the reason for why, for example, this electron has gone up here and isn't down here is due to external energy being absorbed. So it's a very important, well, you get tested on this quite a bit. So there's some kind of external energy that comes along and it gives the electron here a little bit of energy to go up one level. Okay, usually it won't do anything drastic or dramatic. It won't really jump up to say there, because generally that's considered a huge energy energy jump, and usually if that happens, the element will become an ion. Essentially that electron will be lost for good. Okay, so it's usually just the electron jumping to the next shell, but not really going too far for it to become an ion completely. So let's have a look at an example of this. I have a few examples here. Now the important thing with this electron with excited states is that usually they will make sure that they give you neutral atoms. Okay, otherwise, if you try to bring in the confusion of, okay, is this an ion or is this an atom, that will just not be even possible to work out. So they might give you a question such as this: which of the following notations show the electron configuration of a neutral atom in an excited state? And then you have to name the element and explain how you know it's excited. Okay, so now let's have a look. So although I'm just going to get rid of this, although we sort of already okay, so let's say you have this electron configuration. I'm just going to use this table here, although you probably won't be given it. Well, you wouldn't be given something like this in an exam, but I'm just going to use it as a visual. Okay, so let's have a look. 1s2. So there are 2 electrons that fill in the first shell. That sounds right. Okay, we'll go to the next one. There can only be a maximum of 2 electrons, and then it fills the P shell. Okay, so there's nothing drastic going on here. You can see that the 1s shell is full, and then it goes to the 2s, and then the 2s fills up and it's full, and then it goes to the P, 2p. So there's nothing dramatic happening. Like that electron there is not jumping up to, you know, the 3s shell. If that were the case, then yes, that would be considered an excited state. But in this case, where that electron is just filling in the 2p shell, then there is no basis for us to consider that as an excited state. Okay, so because this is a neutral atom, in a neutral atom you know that the proton number equals to the number of electrons. Okay, so what we're going to do is to figure out what element this is. We're just going to count the number of electrons that are present. So we can see that we have 5 electrons being present, which means that this particular atom has 5 protons. Okay, and then we go up to our periodic table and we pick out number 5, and there it is. It's called boron. Okay, so that's the element in this case. So we'll just write that this is boron. And the justification, the explanation of why you know it's not excited in this case is it's basically because, so I write not excited since following normal filling order. Okay, so next one, let's have a look at B. Now, and you can again figure this out. Maybe we'll start off with electron number. So 2, 4, 7, 8. So this has 8 electrons. Okay, so that means it has 8 protons. I'm always skeptical whether I counted this right, but because when it comes to making a video and counting, it's hard to concentrate on both. But yeah, that's correct. So 8 protons. Now we'll have a look at our periodic table. 8 protons means that this particular element is oxygen. So we have identified it as oxygen. Okay, and now a determination of whether this is in excited state or not. Now, considering that you won't have this table that I just used for making your determination, let's consider the filling order. So 1s, 2s, 2p, then it's 3s, 3p, 3d. Okay, so this is how it has to be filled. If you wanted to fill in the oxygen as per normal, you would have to 1s2, then you have 2s2, 2p6. No, it wouldn't be 2p6, it will be remember we have to get up to 8 electrons, so it will be 2p4. Okay, so this p shell is going to contain 4 electrons in it. But look what's going on in this situation. It seems as though one of the electron from the p shell is jumping to the next shell in the third shell and filling in the s subshell. Okay, so really what's happening here, for that electron to jump to a higher state, that means it's absorbed energy from the surroundings. And so therefore you would say that this is in an excited state. Okay, so oxygen is in its excited state. as normal configuration according to the filling order should be is 1s2, 2s2 and 2p4 as we've determined up there. Okay, finally let's have a look at this last one here. So and again, that's 10 electrons there, 12, 13. 13 electrons, 13 protons, because it's a neutral element. And we know that 13 protons, if we look up the periodic table, it's going to be aluminium. Okay? And so what we find is that with aluminium, if we just do the normal, we figure out the filling order, 1s2, 2s2, followed by 2p6, so that makes 10 electrons, then 3s2, and then 3p1. So that should be the electron configuration of aluminium. And you look at that example and it actually matches exactly this. So aluminium is in the ground state. As was boron. Boron was also in its ground state. The only one in its excited state we could see was oxygen in this example. So hopefully that explained the difference between how to determine the ground state electron configuration and how to determine the excited state. For the excited state, if you see electrons not organizing themselves according to this filling order, then you can be sure that they're in excited state because they've absorbed that excess energy from somewhere externally.